By 1943, the Imperial Japanese Army Air Force had brought a logistical paradox into the New Guinea theater. They deployed a high-performance fighter whose upkeep was better suited to controlled workshops into a zone defined by mud, humidity, and isolation. This machine was the Kawasaki Ki-61, designated the Hien, or Flying Swallow. To the Allied pilots who encountered it, it was the Tony. It remains one of the most distinctive engineering deviations of the Pacific War because it rejected the established doctrine of the air-cooled radial engine. That break with doctrine was visible immediately. While nearly every other Japanese fighter relied on robust, round radial engines cooled by airflow, the Ki-61 was built around the Ha-40, a Japanese license-built version of the German Daimler-Benz DB601A, an inverted V12, liquid-cooled power plant. This architecture imposed a different contract on the ground crew. In a radial engine, the cylinders sit in the slipstream, there is no plumbing, no radiators, and no coolant pumps, and the system can tolerate damage and neglect. The inverted V12 architecture flips that logic. The engine is buried inside a streamlined cowling to reduce drag, and survival depends on coolant lines, header tanks, pumps, and a ventral radiator scoop. In return, the Ki-61 gains a narrower nose, higher dive speeds, and better forward visibility, driven by roughly 1,175 horsepower. But the same liquid cooling system multiplies failure points. A leaking seal, a punctured radiator, or a clogged filter is not a nuisance. It can lock the engine solid. This sensitivity makes the Ki-61 an outlier in aviation archaeology. In places like New Guinea, many were lost as much to the friction between high-tolerance engineering and primitive field conditions as to enemy fire. When these aircraft failed, they were often abandoned where they stopped, consumed by the environment they were never designed to survive. Consequently, the recovery of a complete airframe is exceptionally rare. Manufactured number 640 is one of these rare survivors. It rolled off the assembly line at the Kakamigahara plant in November 1943. It was a Model 1B, a variant that would later be distinguished by its heavy armament. Surviving documentation and later museum notes indicate it was immediately earmarked for the Southern Front. It was assigned to the 68th Hiko Sentig, a unit operating out of the WWII area on the northern coast of Papua New Guinea. The transfer of number 640 to the tropics was a one-way journey. From the moment it arrived, the clock began running against its systems. The maintenance crews of the 68th struggled to keep the Ha-40 engines turning. They lacked hangars, dust filters, and consistent supplies of high-quality oil. They were attempting to maintain Swiss watch tolerances with sledgehammer logistics. For number 640, that mismatch closed its operational window fast. It arrived during the monsoon when heat and moisture punished the Ha-40 and the logistics behind it. The records do not show a long combat career. Instead, they suggest a high-performance weapon degrading in place, tethered to a supply chain that had already collapsed. Built for the order of a paved runway in Europe, it was now clawing for traction in the kunai grass of the Torricelli Mountains. 40 years later, the recovery team's question was not only where it ended, but why a valuable fighter, with no recorded combat damage, was left behind. The exact cause of manufacture number 640 going down was never cleanly recorded. One plausible trigger was a small failure inside the Ha-40, oil thinning and heat, a filter choking with debris, or another minor fault that a liquid-cooled, tightly toleranced engine could not forgive. Another possibility is simpler and just as deadly in that theater: fuel starvation. From the cockpit, what follows is brutally simple. The Ha-40 relied on a pressurized oil film to keep metal from touching metal in its main bearings. If that film collapses, the failure does not arrive as a gentle loss of power. It arrives as a hard stop. Once metal touches metal, friction spikes, heat blooms, and the crankshaft can seize, leaving the propeller to windmill or freeze as the aircraft runs out of choices. The pilot was left with a heavy glider. The Ki-61 has a gross weight of approximately 2,950 kilograms and a high wing loading. It does not glide well. The pilot had seconds to select a landing site in the dense terrain of the Torricelli Mountains. He chose a patch of tall kunai grass. That decision may have saved the airframe for a simple reason: tall kunai can act like a buffer. Unlike water, which is incompressible and can hit like concrete at speed, or dense jungle canopy, which can tear a wing apart, kunai grass can absorb energy progressively. The stalks are 6 to 8 feet tall and fibrous. As the aircraft pushes through them, thousands of individual stems add resistance that scales with speed, stretching the impact over distance and lowering peak G load on the structure. The evidence of this interaction is preserved in the propeller assembly. When the recovery team inspected the nose, they found the 3 blades bent smoothly backward around the cowling. This is a specific deformation signature. If the engine had been producing power at impact, the torque would have shattered the tips or twisted the blades forward as they dug into the earth. The backward bend is consistent with the engine not producing power at impact, with the propeller windmilling or nearly still as the aircraft slid to a halt. The pilot egressed and the war moved on. The aircraft remained undisturbed, protected by the isolation of the site. However, while the vegetation hid the airframe, the humidity began a different kind of destruction inside the engine cowling. Kawasaki engineers chased weight savings wherever they could, and engines in the DB601 family used light alloys in a number of cast housings and fittings. In a damp jungle, that choice can become a slow chemical fuse. When dissimilar metals stay in contact in the presence of an electrolyte, they form a battery. Moisture supplies the electrolyte. The less noble metal becomes the anode and sacrifices itself to protect the cathode. Over decades, some light alloy castings can degrade into a chalky residue, leaving fasteners and attachment points deceptively weak even when the outside still looks complete. That creates a trap for recovery. To an external observer, the nose can look intact. Mechanically, the internal connections may be far less trustworthy than they appear. Lift the aircraft the wrong way, and hidden weakness can turn into sudden tearing. The recovery team was not just retrieving an airplane, they were retrieving a collection of parts held together by habit and geometry. When the recovery team reached the site, the aircraft was not immediately identifiable as a specific variant. The jungle had claimed the surface. Lichen, moss, and organic debris covered the aluminum skin, obscuring the painted tail unit markings that would normally indicate the unit assignment. To the untrained eye, it was simply a Japanese fighter. To the forensic recovery specialist, the identity lay in the hard points that could not rot, the serial numbers and the armament configuration. The first task was to establish the manufacture number. Painted numbers exfoliate as the primer fails, but stamped metal endures. By carefully cleaning the manufacturing plates on the internal bulkheads and the tail fillet, the team exposed the stamped digits, 640. Cross-referenced against surviving documentation, the plates placed the airframe in a November 1943 build, part of the late 1943 production run feeding Japan's southern front. However, the specific capabilities of this machine were defined by its guns. The Ki-61 went through multiple armament evolutions. Early models, known as the 1A, carried lighter 7.7mm machine guns in the wings. Later models carried 20mm cannons. The team examined the wing leading edges and the fuselage decking. They found 2 Ho 103 heavy machine guns in the fuselage and 2 more in the wings. This total of 4 12.7mm weapons positively identified the aircraft as a Ki-61 1B, or Otsu variant. It was a configuration optimized for the heavy bomber interception role required in late 1943. With the identity secured, the survey shifted to structural integrity. The primary concern for any recovery of this age is stress corrosion cracking. This is a specific failure mode affecting high-strength aluminum alloys. These alloys obtain their strength from a precise heat treatment process. However, when the metal is held under tension, such as a wing spar supporting the weight of a fuselage, and exposed to a corrosive environment, the grain boundaries of the metal can degrade. The corrosion propagates along these boundaries, creating microscopic cracks that can cause the part to snap without warning when the load changes. The team had to inspect the wing roots. Unlike the Mitsubishi Zero, which used a 2-spar wing design, the Kawasaki engineers had built the Ki-61 with a robust 3-spar wing. This design choice, originally made to support the high diving speeds of the Interceptor, provided a crucial redundancy for the recovery. While the galvanic dissimilarity had destroyed the engine mounts, the wing spars appeared to have resisted the stress corrosion cracking. The 3-spar structure offered a stable platform for lifting. The survey concluded that the aircraft was not just a pile of debris, it was a cohesive unit. The serial number 640 tied it to a specific moment in history. The armament proved its configuration. The 3-spar wing promised a chance to lift it intact. The question was no longer what it was, but how to lift it free without letting corroded bolts become a sudden point of failure. By the early 1980s, the decision was made to extract manufacturer number 640. The work did not happen in a single clean moment. The airframe was broken down on site into major sections first because the terrain and the limits of helicopter sling loads made a one-piece lift unrealistic. In 1984, the Papua New Guinea National Museum and the Royal Australian Air Force supported the removal, airlifting the separated components out to Borum Airfield near Wewak. From there, the pieces could be crated for onward transport. This requirement brought the team face-to-face with the specific engineering of the Kawasaki airframe. Unlike many contemporary fighters which used a bolt-on steel tube truss to hold the engine, the Ki-61 utilized an integral mount structure. The engine bearers were cantilevered extensions of the fuselage semi-monocoque shell. They were built into the skeleton of the aircraft. This meant the team could not simply unbolt a nose section to make the airframe manageable. The fuselage and engine bay were a single continuous unit, 29 feet and 4 inches long, with engine bearers built into the semi-monocoque shell itself. With sling load limits looming, the only practical breakpoint was the wing join, and it had to be approached like surgery. Decades of humidity can lock high-strength fasteners in place, and careless force would have risked permanent damage to heat-treated structure. The team worked slowly and mechanically, choosing preservation over speed, keeping factory geometry intact for whatever restoration might follow. Once the wings were separated, the team faced the critical phase of the operation, the lift itself. This is governed by sling-load geometry. When an object is lifted by a helicopter, it is suspended by straps connected to a single hook on the belly of the aircraft. The angle of these straps is critical. If the straps are too short, they form a shallow triangle. This creates a massive horizontal compression force that tries to crush the fuselage inward, like a can crusher. If the straps are too long, the load becomes unstable and can oscillate, threatening the helicopter. The recovery team had to calculate the center of gravity for the stripped fuselage. The heavy HA-40 engine block was still sitting inside the nose, shifting the balance point forward. The tail section was light and empty. The riggers had to position the spreader bars, rigid beams that hold the straps apart, to ensure the straps pulled vertically, not diagonally, against the skin. They had to cradle the fuselage so that the corroded aluminum did not buckle under the tension. The lift proceeded in stages. The Iroquois hovered over the jungle clearing, the rotor downwash flattening the grass in widening waves. The slack came out of the slings. The fuselage rose horizontally, maintaining its structural shape. It was flown out of the Torricelli Mountains to Borum Airfield. There, the components were crated for sea transport. The extraction was successful not because of brute force, but because the team respected the mechanical limits of the structure they were saving. They understood that in aviation archaeology, the recovery method is as important as the discovery itself. When manufacturer number 640 arrived at the conservation facility, it appeared to be a standard, unpainted aluminum airframe covered in 40 years of jungle grime. The factory records from November 1943 stated that Ki-61 aircraft left the Kakamega plant in natural metal. According to the production documents, this machine should have been silver. However, as the conservation team began the delicate process of cleaning the surfaces, they encountered a contradiction that changed the historical value of the artifact. The team documented the surface as if it were sediment, not a canvas to be stripped. Oxidation and grime can trap faint pigment beneath them, and every surviving patch of paint is evidence. Working with gentle cleaning methods and careful photography, the conservators lifted dirt away without destroying the fragile binders of the original finish. As they worked across the fuselage and wings, a distinct pattern emerged from the oxidation. It was not the solid, dark green typical of late-war Japanese fighters. It was a complex, hand-applied lattice. Ground crews had laid green paint in a weaving motion over the silver skin, reportedly spray applied in the field. Historians know the effect as snake weave, sometimes also called palm frond camouflage. The significance was that it was a field answer, not a factory finish, camouflage applied where the war was being fought. The 68th Sentai was operating from airfields that were under constant attack by Allied bombers. The shiny natural metal of the factory finish was a liability in the jungle. The ground crews had to manually camouflage the aircraft to hide it under the trees. The variability in the weave pattern became a fingerprint of the unit that painted it. The presence of the snake weave forced a critical decision regarding the restoration outcome. In a traditional restoration, the goal is often to return the machine to zero-time condition, making it look exactly as it did the day it left the factory. This would involve stripping the skin to bare metal and polishing it. For number 640, such an action would have been an erasure of history. It would have destroyed the only physical evidence of the unit's daily struggle for survival. The decision was made to preserve the artifact as a combat veteran, not a factory prototype. The conservation effort shifted focus. Instead of making the metal shine, the goal became stabilization. The team applied corrosion inhibitors to lock the remaining paint to the surface. They accepted the fading and the imperfections. By choosing to keep the snake weave, they preserved the narrative of the 68th Sentai. The aircraft does not just represent the engineering specifications of 1943. It represents the operational reality of the men who tried to keep it flying in a collapsing theater. Today, manufacturer number 640 survives because it was removed from the uncontrolled environment of the Torricelli Mountains and brought into conservation and restoration custody. That recovery pulled it out of the jungle. Later, the airframe was moved again for restoration work, including an export in July 2004. Its story is not just that it endured, it is that it kept moving through human hands without losing the evidence stamped into its metal. It provided one of the clearest surviving physical references for the Model 1B configuration. Before the retrieval of this airframe, the specific engineering details of the Otsu variant were known largely through fragmented manuals and grainy period photographs. The recovery changed the academic understanding of the type. Because the recovery team respected the limits of the structure during the extraction, the internal geometry remained true. Historians and engineers can now look inside the wing roots and observe the exact layout of the three-spar design. They can trace the feed chutes of the four 12.7mm machine guns, confirming the logistical footprint of the heavy armament installation. The aircraft serves as a Rosetta Stone for the Kawasaki series. It allows restorers working on other, more damaged airframes to reverse engineer missing components with high fidelity. The preservation of the interior systems is particularly critical. In many recoveries, the delicate control linkages, hydraulic lines, and cockpit instrumentation are lost to corrosion or looting. Because number 640 was isolated by its remote geography and protected by the dense overgrowth, the cockpit remained largely intact. It offers a precise snapshot of the pilot's working environment as it existed in late 1943. However, the artifact requires constant vigilance. The material chemistry that ate at the mounts in the jungle is only paused, not cured. Through humidity control and stabilization treatments, the team keeps that galvanic mismatch in check, an enforced truce that demands constant vigilance. The legacy of number 640 is defined by the tension between ambition and reality. It was a machine built with the precision of a European interceptor, powered by a liquid-cooled engine that demanded sophisticated support. Yet, it ended its service life gliding silently into a patch of kunai grass, defeated not by an enemy pilot, but by the friction of operating a high-tech system in a low-tech war. By saving the airframe, the recovery team preserved this narrative. They did not just drag aluminum out of the jungle. They retrieved the physical proof of a specific technological gamble. The Ki-61 stands today as a testament to the engineering ambition of the era and the operational reality that brought it down. It is a static object, but it continues to teach the physics of flight and the consequences of failure.